I will integrate again. I'll do this part. This is dv. And basically, the rest of it follows in a similar manner. So, okay, du is the same as dx because u is x. dv is d sine x over sine cube x. We could think of it as dt over dt. So to find v, we have to integrate. To find v, we have to integrate this. So the integral t to the power minus 3 dt, which is t to the power minus 2 over minus 2, which is minus 1 over 2 t squared, and t is the sine function. Okay, so this part is different. So v function here was cotangent squared over 2, and there we make the v function minus 1 over 2 sine squared x. A slightly different approach, but in the end, the final results are transformable. You can change one of each of these final results into the other. So this is another option. Actually, I think I would prefer this one, which is why I probably gave you the answer in that form, but this one also works. And it's not always so easy to see if I might use 2 or 3 different methods, which method is the best. It's not always very easy to see. All right. Now, probably it's time to start on the new material. My hands are completely wet and dirty. Okay, I'm leaving that for a moment. Alright. And the next topic, the final big method, integrating rational functions. And as I already said, there are hundreds of methods of integration, each meant for a different kind of functions, and we have by no means even close to discussing all of them. If I wanted to discuss all of them, I should spend, well, the whole semester probably, because there are really many of them. How to integrate functions that are irrational, functions containing radicals, functions containing too much trigonometry, and so on and so on. And then there will be always some functions that do not allow any specific method to be used, and you have to improvise, combine methods. But the final big method, integrating rational functions. What is a rational function? A rational function is a function in the form of an algebraic fraction or ratio of 2 polynomials. So it will be polynomial, let's say p of x divided by the polynomial q of x. A rational function. For example, 3x squared minus 2x plus 7 over x cubed minus x minus 10, something like this. The ratio of 2 polynomials. That's what a rational function is. A rational function is the ratio of 2 polynomials. And just like with numbers, when we have numbers, we can talk about proper fractions and improper fractions. And I already mentioned this last time, I think on Tuesday, proper fractions, improper fractions. A proper fraction numerically, if we talk about numbers, is a fraction where the numerator is less than the denominator. A fraction is improper if the numerator is the same as the denominator or perhaps greater than the denominator. So proper fractions less than 1. The value is less than 1. Improper fractions, the value is greater than 1 or equal to. With rational functions, with algebraic fractions, what we call proper is a function where the power of the denominator is greater than the power of the numerator. In other words, if the exponent, the highest exponent here, is greater than the highest exponent there, then it's proper. The denominator is, well, so to say, greater than the numerator. If the powers are the same, or if we have a higher power in the numerator, then it's improper. And we will focus on proper fractions. So first of all, the first step, if this is an improper fraction, we divide the two polynomials so that we can separate. We can change it into, for example, some other polynomial as we divide, plus some remainder polynomial over the same old denominator. So if the fraction is improper, we can do this so that we create a proper fraction. And the problems with integration, of course, here we have no problems. Polynomials give us no problems at all. The problems with the integration start when we are considering integrating proper fractions, something like this, or worse, or better. Depends on the number of the powers. So first of all, there are four basic types of elementary fractions that we know how to integrate. Okay, I know how to integrate. And you more or less could know, except for type 4. An integral of type 4 fraction is, well, 2 pages or so. Okay, so let's suppose now that we have a proper fraction, which means the degree of the denominator is less than or equal to the degree of the degree of the numerator is less than the degree of the denominator. So let's suppose we have a proper fraction. Let's look at some basic types of proper fractions. Basic types of proper fractions. And we will call them elementary or partial fractions. Elementary fractions, there are several reasons why we call them elementary fractions. First of all, because they can be integrated comparatively easily, they are comparatively simply to integrate. Secondly, because it turns out that any proper fraction can be expanded into a sum of elementary fractions or resolved into elementary or partial fractions. Okay, basic types. Type 1. Elementary fraction, some number a divided by x minus some other number a small. For example, 2 over x minus 3, or 7 over x plus 10, things like this. That's a very good partial fraction because we know how to integrate it. What is the integral of this, by the way? So, for example, if we have 3 over x minus 4 dx, if we need to integrate a type 1 fraction, it's 3 natural logarithm of x minus 4. Because we remember that inside the differential, we were allowed to do this. And that makes it a simple logarithm. Okay, so type 1 is very simple. We are absolutely happy if we only have type 1 components. Are we happy often? No.
Because you're not nice.
Type 2. Type 2 partial fraction is again in the form A. Oh, okay, I will write another letter so that simply you don't get too confused. So I'm using another letter, but it's still the same form, the same idea. In this case, we have not simply x minus a, not simply a linear binomial in the denominator. We have a power. We have a power. N is not equal to 1. So n is greater than 1. It's still a natural number. Still a natural number, positive integer. So, do we know how to integrate these? For example, integral of 5x plus 2, let's say cubed, dx. This is 5 times x plus 2 to the power minus 3 dx plus 2. Again, I'm adding the number I like inside, so we have to integrate power minus 3 means add 1, divide by the new denominator.
Minus 3.
What?
Okay.
What? This is plus.
Yeah, it's minus 3. First of all, the denominator and then we check the. We have 5, we have x plus 2, integrate power minus 3, you get minus 2, and you have, remember, you have to divide by the new exponent. Plus c, which means we have minus 5 over 2x plus 2 squared plus c. So yes, we do know how to integrate those two. A little bit slightly more complicated, but not much. So again, quite possible to integrate. Type 3. Sometimes we just don't have linear options in the denominator. Sometimes you simply cannot factorize into such linear factors. Sometimes you simply get a quadratic trinomial with negative discriminant. We call them positively definite trinomials. And so we might have something like cx plus d over x squared plus bx plus q. I'm writing the simplest form where the discriminant of this is, negative. So I'm writing, okay, I will actually use the delta. Delta is negative. The discriminant of this quadratic is negative. So this quadratic form is positively definite. It's positively definite. So we cannot factorize it further. We cannot factorize this further into something like this. Otherwise it would be much simpler. We cannot. Of course we can if we want to use complex numbers. But the theory of the functions in complex numbers is too complex for you at the moment, I guess. So this might have some problems for integration, but I will show you an example. Basically, it could be more complicated, it could be slightly more difficult, and we will discuss that probably next Tuesday, because there will be, again, probably not enough time for that. So let's have a look. Let's imagine, for example, 2x plus 5 divided by x squared plus 3. Okay, no, 3. Let's say plus 6x plus no.
12.
25. 25 will be good enough. 9 plus 16 is good. Okay, dx. How to integrate this? First of all, we have to notice that if we denote by u the function x squared plus 6x plus 25, then du will be 2x plus 6 dx. We almost
have it. We almost have it. We have plus 5. We don't have plus 6. We almost have it. So I'm simply showing a simple example. This is not, perhaps it's not the best, well, it's not the most comprehensive, but at least it gives you an idea. So to make plus 6, I write plus 1 minus 1, and I split it into two integrals now. So it will be integral 2x plus 6 over x squared plus 6x plus 25 dx minus integral, now it's only this, 1 dx over x squared plus 6x plus 25. This is, well, this case is pretty simple, but this is what we basically do. We split type 2 partial fraction into two more or less familiar integrals. So first of all, we have a look at what we might need here to make this into a logarithm, because this is what's happening here. So this now is going to be integral du over u. So du over u. So this is the logarithm of this function. So that's not so bad. So what about this one? Do you remember how we did this? This is not very difficult. But again, you have to know how to do this. We will need to work on type 3 partial fractions anyway. So that's where the time will go next week. With these, it might be a little bit messy with these. It can be messy with these, not necessarily so, but it depends on the numbers.
Like a full square.
Okay, so I can complete the square for this. I know that this is x plus 3 squared plus 9 plus 16. So I complete the square. I separate the perfect square, and then I have another square, and this looks like arctangent now. This looks like the arctangent thing. So for the first integral, for the first component, I have natural logarithm of x squared plus 6x plus 25 minus integral of dx over x plus 3 squared plus 16. Now I add 3 inside the differential here. So at this point I have dt over t squared plus 16, this type of integral. Here now I have this kind of integral, and that's a standard integral, arctangent of t over 4, 1/4 in front of it. So this is the standard integral, it's 1 over 4 arctangent t over 4. So I'm just writing it in this form. So it will be ln x squared plus 6x plus 25 minus, now this will be 1/4 arc tangent x plus 3 over 4 plus constant in the end. So this is what I get when I integrate type 3 partial fraction. Basically, in general, the type 3 partial fraction, the integral of type 3 partial fraction, results as a sum of two integrals, logarithm of the denominator plus or minus arctangent of something that is constructed from the denominator. This can be actually constructed from the denominator, this expression x plus 3 over 4. So this is how we generally do type 3 partial fractions. We will probably need to discuss these for a separate lecture, or at least half of a separate lecture, because this is again a special case. We have to look at integrating this. We have to look at integrating this. Type 4. Can you guess?
How many pages we need?
It's on your page. Type 4, well basically my students at school can guess. If they have looked at this, then it will probably be mx plus n, again a linear expression, and then you will probably have some power there. That's what they generally say, and it's, well, it's, type 4 is this. So if you have not simply the positively definite quadratic in the denominator, but you have a power of it, it still cannot be factorized any further. About the denominators, I'm not going to show you how to do this because that would take me more than the rest of the lecture. Or maybe the rest of the lecture, but if I had to go slowly, then it would take more. Type 1, type 2, type 3, type 4, and it appears that any rational function, any proper rational function can be resolved or split or expanded into a sum of such fractions, into a sum of only these 4 types of partial fractions. It can be proved, but that's done in the algebra course. We are doing calculus now, so we have no time to prove that any rational function could be split into these in one and only one way, by the way. This resolution, this expansion is unique for every rational function. You cannot do it in 2 different ways. But that's proved in the algebra course. Not here.
I have a question.
Yes.
The point, the right point, right side of it. There is an x squared plus 6x plus 25.
Yes.
No, right.
Yes.
Yes,
Here, everywhere.
Now the word we see is plus 3 squared plus 6x. Is it equal to the...
It's the same.
But where is the 6x there?
You took the 6 into the square.
There is a formula taught in the 7th grade algebra. A plus b squared equals a squared plus 2ab plus b squared. So, yes, I see x squared plus 6x. I understand that 6x is 2 times 3 times 6. So the third term would be 9. The last time anyone asked me this was, I know, some 17 years ago in the United States, where the kids generally don't study geometry, so they don't have very good logical reasoning. But that's an interesting question. Where did the 6x go? Where did you hide it? Well, like this. If I take a newspaper and I fold it, I hide it. Just like that. It's what's happening here. This is a newspaper, I'm folding it, so it's hidden now. More questions? Yes?
Yeah,
So what about that?
four rational fractions could be split into the sum of this kind of.
Of 4 of these 4 types, any rational fraction can be split into a number of this type, of these 4 types. You don't need anything else. Type 4. Well, those who really want type 4 have to wait until probably next time. I can bring you the solution for type 4 integral, but I'm not going to do it in public. I'm not going to do it.
Why not?
2 pages?
2 pages.
2 pages for one integral?
But will you give us type 4 for the test?
No, no, I won't. But all right,
Whole separate test.
I will have to translate it. I have it.
Latvia.
In Latvian, yeah, I have to translate it so that I can write it out. I can translate it and send it to those who want it. But it's.
But in type 4, the n must be also more than 1. And
Yes, because otherwise it becomes type 3. All right. So now, how to resolve a rational function
into partial fractions. When we have this improper fraction, so we assume that now we have divided out the polynomial, we only have a proper rational function. What we do is we factorize the denominator. We factorize the denominator as much as possible. So we still have this, and the denominator will become x minus a, x minus b, perhaps to some power n, perhaps it will be x minus c as well, perhaps it will be something like this, and so on and so on. So we factorize the denominator. And then, for each factor, we get a type 1 or type 2 or type 3 or type 4 elementary fraction. In other words, now I can resolve this into a sum constant a over this, plus some constant perhaps c over x minus c. So every single linear factor creates a type 1 fraction. The bad part at the moment is we don't know what these numbers are. But we know that there will be such fractions. Now, every multiple linear factor creates, I'm sorry to say, n type 1 and type 2 fractions. In other words, this would become b1 over x minus b plus some other constant b2 over x minus b squared plus and so on until we reach bn over x minus b to the power n. So you see, as soon as we get a power of a factor, a multiple factor, it at once, immediately, it will provide us with n fractions. The good news is that quite often many of those capital B values become zeros. And I'm not going to give you x minus 3 to the 5th power, for example, so that, no, you won't have 5 of these. But the thing is, if we have a multiple factor, it actually resolves into n type 1 and then type 2 partial fractions. Sadly. And then of course for each factor like this we get something, okay, ex plus f over x squared plus bx plus q. And if we have an nth power of such a factor, if such a factor is repeated, for those the same thing happens. Again, n type 3 and type 4 partial fractions. So if I had something like this, for example, cubed to the 3rd power, then the result would be such one fraction like this, another fraction like this, but with x squared plus bx plus b squared, and the 3rd one with a cube. So yes, so what you can hope for now is that the rational function is simple enough that there are not many of these. We are not going to do many of these because, well, there's no purpose for me to put examples with really many factors in the exam or even in the test, because what matters is that you know what to do theoretically, in principle. I don't need you to show me that you can do something with 10 factors. There's absolutely no need for that. Okay. Let's have a look at those examples. X plus 10, x squared plus 2x minus 8. Okay, so if I want to integrate this, for example, I know that x plus 10 and the denominator can be factorized. X
plus 4x minus 2. Which means that basically this should become a, some unknown coefficient, a over x plus 4, plus some unknown coefficient b over x minus 2. So these would be very simple to integrate. Now the problem is, how do we find a and b? We are using something that's called the method of indefinite coefficients, or the method of uncertain coefficients. We don't know what a and b is, but obviously if we put these back on the same line, we should get x plus 10 in the numerator. So this means that if I multiply this denominator and numerator of the first fraction by x minus 2, and the denominator and numerator of the second by x plus 4, I can bring them on the same line. So x plus 4, x minus 2, a x minus 2, plus b x plus 4. Now the thing is, for every value, for all values of x, this has to be the same as x plus 10, because we are working with a very specific fraction. So what we know now is that a times x minus 2 plus b times x plus 4 is identical to x plus 10. I'm putting this identical equality sign to stress that this must be true for all values of x. For all values of x. Now let's choose some values of x and make equations. So what are good values for x to choose? 2, of course. For x equal to 2, I have, this becomes 0, this becomes 6b, and this becomes 12. So I can see that b has to be equal to 2. It's not so bad. And another good x value? Minus 4. Because with that, this becomes 0. And we have minus 4 minus 2 is minus 6a equals minus 4 plus 10, 6. So a is minus 1. And there you go. And there you go. So this fraction now is a is minus 1. It's minus 1 over x plus 4 plus b is 2 over x minus 2. And if I need to integrate, I integrate these. Minus 1 minus logarithm of x plus 4 plus 2 logarithms of x minus 2. The integral will be easy. So of course, if we have a nice quadratic in the denominator, which can be factorized easily, then this is not difficult to do. The difficult situations, of course, arise when we have something more complicated. For example, all right, the second one, 3x cubed minus 5x to the 5x squared plus 7x minus 3 over x squared plus 1 times x minus 1 squared. I'm not asking anyone to integrate at the moment. I'm simply, so you see, in most situations, if you have to factorize something by yourselves, it will be simple. And if not, I will spare you the algebra and I will give you the factorized version already, so that you have no problem. This is a proper fraction, square, and this is a square, so the degree of the denominator is 4, and this is a third degree polynomial, so it's a proper fraction. So this should become, now, because this is a quadratic, okay, so p is 0, we don't have anything times x, but it's still a quadratic. So this would be, for example, ax plus b over x squared plus 1. Now, this is a double with a double factor, which means I will have two elementary fractions from this. It will be c over x minus 1 type 1 plus d over x minus 1 squared type 2. It's this. So for x squared plus 1, we get type 3. And for x minus 1 squared, we get type 1 and type 2. So now again, to get everything on the same line, I only need 5 minutes to finish. X squared plus 1 times x minus 1 squared, going back to that denominator. This means x minus 1 squared. This means x minus 1, because 1 is there already, times x squared plus 1. And this needs x squared plus 1 only to get the same. So we have ax plus b times x minus 1 squared plus c x minus 1 x squared plus 1 plus d x squared plus 1, and it has to be identical to 3x cubed minus 5x squared plus 7x minus 3. Now this is long. But we can do some things. For example, if we take x equal to 1, then the first two products will disappear. So this has to be true for all values of x. So if I take x equal to 1, then this whole part disappears, this whole part disappears because I have 0 there, and we only have 2d. We only have 2d. So 2d equals, and if x is 1, then I have 3 minus 5 plus 7 minus 3 is 2. So d is 1, at least something. So now we will be able to use these one. Now the problem is, we don't have any good other values, for good x values, because we cannot make anything disappear anymore, because x squared plus 1 will never be equal to 0. But we can take some other, let's say, decent values. For example, we could take x equal to 0, which will make things simpler. So if x equals 0, then we would have, from this we only get b, because this disappears, and minus 1 squared is 1, so this whole term becomes simply b. If x is 0, then this is 1, this is minus 1, so it's minus c. And if x equals 0, this is simply d, but we know it's 1. So I'd rather put in 1 because I have it already. On the right hand side I have minus 3. So that will be an equation. If I get one more equation with b and c, I can find b and c. So what other x values could we choose? What other x values could be nice? Minus 1 perhaps. 2. Because for 2, this becomes 1, this becomes 1 again, more or less easy. So if x is 2, I have, this is 1, so this becomes 2a plus b. 2a plus b. If x is 2, this is 1, this is 5, so that's 5c. If x is 2, here we have 5 times d, which is 1, is 5. And if x is 2 here, 8 times 3, 24, minus 20 is 4, plus 14 is 18, minus 3 is 15. And yes, we could take minus 1. We could take minus 1, see, just to see what happens there. I have no idea. So it's minus 2, and then you square it's 4. So it's minus a plus b times 4. That would be minus 4a plus 4b. Now this part is minus 2, and this is 2, so it's minus 4. minus 4c. This part is 2d means 2. It's just 2. And if x is minus 1 there, minus 3 minus 5 is minus 8. Minus 8 minus 7 minus 15. Minus 3 minus 18. And now we have a system of 3 equations with 3 unknowns, 3 variables. So b minus c equals minus 4, 2a plus b plus 5c equals 10, and minus, I think we can divide everything by minus 4 actually. We can divide everything by minus 4, so I have a minus b plus c equals minus 20 divided by minus 4 is 5. Now it's in a more decent shape, I guess. If I add the first and the third equation, I get a is equal to 1. If I add these two equations, these two cancel out. A equals 1 from this. If a equals 1, then we could write b minus c. A equals 1, then b minus c is minus 4. 2 carried over, b plus 5c is 8. So subtract this minus this means 6c equals 12. So c is 2 and b is minus 2. Okay. So as a result, I can write that this is ax plus b. A is 1, b is minus 2. So x minus 2 over x squared plus 1 plus c is 2. 2 over x minus 1. And d is 1, so it's plus 1 over x minus 1 squared. So yes, this process can take a bit of time. And we will return to these tasks, to these rational functions next week. Okay.